very much. It's a great pleasure to be back in Japan. It is actually my 4th visit to Japan, I think I counted correctly. And I noticed that every time I came to Kyoto, and each of the 4 times. And of course, it's a real pleasure and a great honor to participate in the activity of the Super GU. And I wish you all the best for the continuation of this program. It's, of course, a real pleasure to be back with my friends and colleagues here, Professor Ozawa, Professor Izumi, and a few others that I see in the audience. Okay, so the main subject today of the talk is quantum expanders. So quantum expander is, of course, as you will see, a non-commutative version of the notion of expander. And it was, the term at least, was introduced fairly recently, the 07, by Hastings, who's, I guess, usually described as a theoretical physicist, a mathematical physicist. Benaroya and Tashma, I think Hastings was at Microsoft, I don't know if he still is. Benaroya and Tashma are computer scientists at the Weizmann Institute. They were interested in relations of this notion to computer science and also to quantum information theory. This has some connection with that, and I think it's been sort of taking momentum in the literature in quantum information theory and computer science. So it's a bit, unfortunately, heavy to swallow as a concept because you see there are all these dimensions that come in. So I'll try to sort it out. So we have a small n, which I will refer to as the degree of the quantum expander, and then a capital N, which will go to infinity, you have to think of this capital N as being big. So it's a big N. And this object is, what matters is we have a sequence of unitary matrices of size capital N times capital N. And we assume that we have a spectral gap condition, which is written here. That is, you have this inequality restricted to matrices X of trace 0. You obtain an inequality which is better than the triangle inequality. You see, these multiplications are unitary, so they preserve the norm, which we use here, which is the Hilbert-Schmidt norm, or the Euclidean norm on c to the nth squared. Okay, very simple norm. I think in representation theory, they call it the Frobenius norm, but I call it the Hilbert-Schmidt norm because I care about infinite dimensional objects. Okay, and so that's it. That's what we mean by a quantum expander. Let me just make a restriction that, in fact, we don't really need usually all dimensions, and what matters is just to have a sequence of arbitrary large dimensions, which is similar, as you will see, to expanders. And then I'll call this epsilon expander. So epsilon always, for me, will be the spectral gap, which I choose to normalize like this. This is not universal, but I choose to do it like that. Okay, so it's important to get the notation right. So I will constantly use these expressions, but everything will be matrices. So it's really elementary. There should be no problem to follow what I'm doing. The important thing maybe to write is this, that if I have a matrix Aij and then another matrix BKL, so then when I write this guy, okay, so this guy means this is the matrix, so A is this matrix, B is this matrix, so this guy will be the matrix Aij BKL, okay, but this matrix now will have as the line index this pair and as column index this pair. So these matrices are n times n, And now this matrix is n squared times n squared. And actually, I will use constantly expressions like this, which just means that I take this complex conjugate here. So everything is very simple here. You have all this explicit. And the other thing you need to absolutely remember throughout the talk is this last line here, that every time I take the norm of this guy, it's always like this. I look at this linear transformation from Hilbert-Schmidt norm to Hilbert-Schmidt, okay, and I compute the norm. So Hilbert-Schmidt is nothing special, right? So the norm of this A, which I call 2, is just this. Okay, so that everything should be, I hope, clear. And if I'm forgetting something or confusing you, please ask. So you see that we are really interested in the spectrum of this operator, or at least the spectral gap of this operator, which incidentally satisfies, nice properties. So it takes positive to positive. The unit is fixed, and it's also fixed by the adjoint. So you can recognize here properties which are classical properties of the Markov operator, for instance, in Markov chain theory, or random walk theory. So this object for us will be like a non-commutative example, analogous with analogous properties to the usual Markov operators. So what we care about is things like this, which have this spectral gap here. And I don't know if I explain what is this P here. It's just P is the projection to the multiples of the identity matrix. So 1 minus P projects to the subspace of matrices with a 0 trace, projects orthogonally to this subspace. OK, so I think I've said enough. This is what we have. We just are interested in producing such things. Little n, again, is the degree. Epsilon is the spectral gap. And in fact, as you will see, it is not so easy, especially at this stage. It is not so easy to produce examples. I will show you that the examples of quantum expanders actually can be derived from example of expanders. So now let me connect this to expanders. So why can I say that there are non-commutative versions of classical expanders? So what are expanders? I restrict expanders a little bit in the sense that I want to not consider general graphs, but just, Cayley graphs. And it fits this pattern. It's analogous to that, not to the general graphs. So I look at Cayley graphs in groups. And let me restrict also a little bit to not worry about bipartite questions, etc. So I just have the spectral gap to be symmetric, like written here. So certainly what I'm writing here corresponds to a very classical example of expander. So you have an expander when you have a finite group, which will have arbitrarily large cardinality. So it's a finite group, but the number of elements tends to infinity. You have to think of it like that. The number of generators is this degree, which is fixed, S. And then the norm of just the sum of the translation by the generators. So lambda G is the left regular representation. So lambda G takes L2G to L2G. The group is finite, but we can write all this. And this takes a basis element delta T is taken to delta ST by lambda G S. OK, so, well, one way to see that we have a connection is to write this elementary fact that if we restrict to diagonal matrices and we look at our transformation on diagonal matrices of trace 0, then this is exactly the same thing as this when we take for the uj these unitaries here. But that's not so interesting. What's more interesting is what's coming next with the decomposition into irreducibles. Let me just here insert a little bit of background for those of you who haven't heard of expanders. It's the notion that's been found tremendously useful for actually applications of mathematics. It appeared, well, the history is a bit now complicated, but essentially it appeared in the first examples, explicit examples of the kind that is here. Cayley graphs appear in Margulis' work, and it uses deep number theory, and even deeper in the work later of Lubotsky, Phillips, and Sarnak, who developed the theory of Ramanujan graphs, which have the optimal spectral gap, the really largest spectral gap possible. And the important thing is they obtained explicit constructions of such objects. But in fact, there are also very useful random methods to construct these objects. And all that I'm doing relates to the random method. So I'm I will be constructing by random methods quantum expanders, although they are not exactly chosen at random, but they are constructed using random methods. So in case you're interested, I wrote here 2 very important, very nice surveys on the subject. And I said the history is complicated because some time ago, some people noticed that very early papers of Kolmogorov actually had the idea of expanders in there from the 60s. And it's Kolmogorov and Bldg. It was a big surprise, but this came up recently. Okay, so now let's look at how we can pass from expanders to quantum expanders. So we take a finite group, and we assume we have the expander condition, which is here. Now, take this representation, lambda g, which is here, left regular representation. Of course, the classical thing is that it decomposes into irreducible. So take an irreducible pi, and now look at the unitary, which is associated to these generators that we fixed here. So we have an n-tuple now, little n-tuple of unitaries. And this is a classical, this is an epsilon quantum expander with the same epsilon as here. The reason for that is very simple. When we look at this representation, okay, which corresponds to this applied to the generator, and we restrict it to the orthogonal of the identity, this representation decomposes into irreducible because we're on a finite group, any decompose into irreducible. But if we remove here this fixed vector, it will have to decompose into non-trivial irreducible. And the non-trivial irreducible are all inside the left regular representation because it's a finite group. So we have all the irreducibles inside the regular representation. So just this one line explains this connection here. So already you see that from an expander, you will get quantum expanders because there's just a little point to add, but simply because expanders give you very, very large groups, finite groups. These will have, so this is the point that let me shift on that. You can show that this will necessarily have arbitrarily large irreducible representations because the spectral gap forces that, but this is a point, let me leave that out for the moment. It will be clear later. And so you just choose irreducible representations of large dimension, and in principle, you can produce quantum expanders. Okay, but there's more, which is important for what I want to present. Another connection, another important property of irreducibles here is that if you have 2 irreducible representations which are distinct as representation, it is not distinct means not unitarily equivalent, okay, of course. So if you have 2 distinct ones, and now you play the same game, that is, you apply them to these generators, and you form your unitaries associated to these 2 representations. So then what you will get is a condition where you don't even need to worry about restriction to the orthogonal of the unit, because the whole representation pi tensor sigma bar, by Schur's lemma, that whole representation does not have an invariant vector. Because if it had an invariant vector, they would be equivalent, and you're assuming they're not equivalent. So since it doesn't have an invariant vector, this is included again in this non-trivial part of the left regular representation. And since it is included, that means that this representation has this matrix as a block matrix somehow. So every norm that you compute with this will be less than the same norm computed with this. Okay? So it tells you that the norm here will be less than the same thing where you replace this representation by this one. And this is then the spectral gap of the expander.
One stupid question. You could have multiplicities in this tensor product. Is this a problem or is this not?
Not for the norm, because I take the operator norm, so it's not a problem. Okay. Okay. So here is a first point, which is actually one of the reasons why I became hooked on the subject of quantum expanders. It's a very nice question that I've heard from Wigderson in a talk, and I've heard him actually repeating this question several times, but it's not very clearly in print, although it appears in some lecture notes taken by students at some place. And it's related to a paper of Wigderson, who's a specialist of expanders, and Meshulam. And the problem is this. It turns out that there is a bound that you can show, which appears in a paper by Delart, Robertson, and Valette, and also implicitly in an earlier paper by Simon Wasserman, and which is the following bound, which is written here, which I have to explain because it's important to get it right. It says the following. If you're in this situation, so you have an expander in your finite group. So you have a fixed degree, little n. Little n is fixed. Epsilon also is fixed. You fix the spectral gap. But the group is arbitrarily large, okay? So you have no bound on the group. Then automatically you have the following bound on the number of distinct irreducible representations that have dimension less than a certain number, n prime, arbitrary, and the bound is like this, is, let's say, sub-Gaussian, because you have exponential n prime squared that appears. So this is a bound which is, a little bit surprising. It's a bound that, actually, in the paper of Simon Wasserman, he worked on these bounds for groups with Kashdan property T. It's also true for groups with Kashdan property T that you have this. It's not at all obvious. You see, in Kashdan property T, you have infinite groups, and this theorem says you have only finitely many irreducible representations of dimensions less than any given bound. Okay, so there's actually it's surprising at first glance when you don't know the arguments for that. So here I prefer to work in the finite group setting, but you have to remember that since the cardinality of G is arbitrarily large, then this makes sense, hopefully. Okay, so the main result that I have on quantum expanders actually is this, and it says two things. Roughly, well, it says that there are many quantum expanders of arbitrary spectral gap, and this is not so surprising because random arguments actually, random methods from Hastings' work that I will mention in a moment actually show this. But the important point for me and the important point for all the applications I have is that I can actually exhibit a family of epsilon quantum expanders which have this uniform separation of the same kind that had these quantum expanders from distinct irreducible. Okay? So this is the important point. They are uniformly separated by delta, which is also arbitrarily between 0, 1, and this separation is written in the last line. And they are also all epsilon quantum expanders, which means that we have this first inequality. And then the key point, the central point, is that we have this, that is their cardinality is optimal, at least asymptotically optimal. That is, this number is the same number that appeared in the previous upper bound of Wasserman, Robertson, Palette, etc. So, of course, you could say that it's not optimal because I don't have the optimal beta, but I mean, we are kind of, this is asking too much. I mean, we just want the asymptotic optimal when this capital N goes to infinity. Okay, so let me show you the application of this, which is almost a reformulation, actually, in the setting of this problem of Wigderson. It is, I'm not claiming that I'm doing anything significant to the problem of Wigderson. I'm actually just looking at a different problem. I'm looking at the same problem for quantum expanders. But what's nice is that it is really the analogous problem. And then the analogous problem, in this analogous situation, you have really the complete answer of this asymptotic. Okay, so the situation is this. We now can freeze things like that. We look at any group, and we look at a finite dimensional unitary representation of this group G. So that could be, of course, that could be a finite group, and we could consider the left regular representation on this group. But we just look at an arbitrary representation, pi, and now we assume that the representation pi tensor pi bar, which I've already explained the bar before, it's in this sense, has a spectral gap of the same kind, but now there might be a bigger invariant subspace. So we look at the invariant subspace for this representation pi tensor pi bar, and we compress, or we restrict to the orthogonal of this invariant subspace. But other than that, the situation is similar. So the same argument that proved the previous result works in this setting. You have the same bound. That is, the number of distinct irreducibles that appears has this bound here. I should have written n prime to be consistent. I just somehow wrote n here, but it was like this, n prime before. I've reserved capital N. Okay, well, I've reserved n here. Okay, so in other words, if your little n and epsilon is fixed, you have a growth on the number of distinct irreducible that can appear in this representation pi when you decompose it as a direct sum of irreducible in the absolutely standard way. And the bound, again, is exponential big O of n squared. So the point of looking now at quantum expanders is that, in fact, a corollary of my main result, that I can produce lots of quantum expanders with a maximum cardinality and with somehow a uniform separation, this yields the corollary which is here, which is that exactly now this growth is optimal. That is, we have a lower bound. It is exactly the optimal possible growth. So this, of course, requires to produce, a representation pi with a fixed n, with a gap epsilon, which can be arbitrary between 0, 1, and which has this as large as this number of distinct irreducible subrepresentations. And so there's no mystery. The proof of the corollary is direct from the main theorem. You just take a direct sum of this large family of separated n-tuples, and it produces this. It is exactly, it's a direct corollary, which is more or less equivalent, except that I can play with epsilon and delta and have more. In the theorem, I have a little more than in the corollary. So the connection with Wigderson's question is simply this. You see, what they are interested in expanders is not this representation pi that I've written, but representations that are the left regular representation of a group. And so the difficulty, of course, is to produce not representations as I do here to show this lower bound, but to produce groups, finite groups and expanders. And of course here, the group generated by this quantum expander is going to be infinite. And it's far from answering the question. But still, it gives some sort of idea that, well, perhaps the bound to be expected is larger than what specialists thought. Schulen and Vigdisson, in their paper, have a lower bound somewhat close to exponential of capital N, but actually the degree is not bounded in their examples. So the degree grows very, very, very slowly, and they produce a lower bound of e to the n, but it's actually the examples seem to be very far from, all the known examples are very far from this. Okay. So let me now give you an application which is closer to the interest that I have for quantum expanders. I'm doing things using quantum expanders, and I'm trying to require of you, as little as possible definitions, notations, and so on. So let me use a trick. So I use a notational trick. So let me use this trick that I want to use a notation that's similar to the scalar product, except that now you have to accept this idea that's very much the quantum idea, that we replace scalars by matrices. So the coordinates of my vectors A and B now are matrices of size capital N, big size, but okay, so in general, maybe we could take operators, but today I'll restrict everything to matrices. So this scalar product lives inside this large matrix space, and of course the norm here that I'm taking is, like I explained before, out there, right, or earlier, is the norm in this space. The norm, it corresponds to the action that I wrote, the operator that I wrote. It's the same as before. So Hagerup actually proved a version of Cauchy-Schwarz inequality for these expressions that's fundamental for what I'm discussing now. And what I have in mind is to, without explaining too much, just say this. This Cauchy-Schwarz inequality leads to a proof of the existence in operator space theory. I'll come back to operator space theory just in the last minutes of the talk, but now I don't want to say much. And it leads to a notion which is the analog of Hilbert space in operator space theory. So it's the following. You can show that there is a system of operators, bounded operators on Hilbert space, which I denote here theta j, which is an analog of the orthonormal basis of Hilbert space in the following sense, that if I take an expression like this, and I take the norm here, so here this is the norm, just to be complete, I have to explain this. So this is going to be the norm in Mn tensor B of H, but this we identify with Mn of B of H, and so this is the norm that I'm taking here. Xj is a matrix, theta j is an operator, so this expression is in this space, and I take the norm of matrices with entries in B of H.
Just a reminder, what was theta j?
Theta j exists. That's a sequence. I'm now asserting a fact, which is there is a sequence in B of H. One can prove this. It's something I proved. It turns out to be fairly easy. Okay. There is a sequence in B of H that satisfies this. And so there is a space which I call OH, which is the linear span of this sequence, that is actually in some sense characterized by the property which is here. And this space, but I don't want to say more, corresponds to Hilbert space in operator space theory. It is the unique self-dual object in operator space theory, but it is very easy to imagine what it can be once you just read this line. It is clearly an object which is very, very much analogous to Hilbert space. And so let me now show you the use of quantum expanders in there. So it turns out that an important and nice technical point that I've been using to prove the next result is very much, is what I like, is that it's very much a geometric fact, but you have to sort of accept, this postulate that numbers are replaced by matrices. So the whole geometry is now done accepting this, this idea here. But we have the ordinary Hilbert space here that plays a role. So this ordinary Hilbert space script h is just given by this norm, which is the usual Hilbert space norm. Just I normalize it by little n times capital N in order to be sure that if I have unitaries, so there is a mistake here. So I think what happened, something is probably wrong somewhere. Something wrong coming somewhere, but anyway, in this line, what I mean is unitaries, I've done the normalization. So in this line, the unitaries have norm 1, and then, okay, let's see, let's go on. And then this is, here, this is just a notation. We have unitary matrices acting by left and right multiplication on little n tuples of matrices. And it turns out that the quantum expanders, so here the point A is a quantum expander. These are unitaries, so normalized by dividing by square root of n. Okay, that gives the normalization in this scalar product. So this will be of norm 1 for calculations of this kind. So this is, A is a point in this new unit sphere according to, or maybe I'm moving too far in this direction. So it's in the sphere, and it has a certain smoothness. This point has a particular smoothness property, which is expressed just by the last line. And this point here in this last line is actually an important technical point in the results that come after this. So it corresponds to, what's nice is that it corresponds to a fairly nice picture from classical Euclidean space. You know that if you have a point A here, and if you want to norm it, okay, you know that there is a unique norming functional on the Hilbert space, on the sphere of Hilbert space. Each point has a unique norming functional, but also this property of smoothness is also uniform in the sense that if you have any functional that almost norms your point, then it has to be close to the unique functional that norms. So it's sort of a uniform smoothness, so it's dual to uniform convexity. And here we're in a self-dual setting, so in fact, both properties play a role. But in the end, you see that it's just this, and it's analogous, except my conclusion will be in this normalized norm. Let's see, something is wrong. So I think for this to be correct, I probably should not have normalized here. I think this is my mistake. I should not have normalized here. Okay. And yeah, there is a detail here, which is that you see A becomes close to, you would expect A close to B, which is the naive picture which corresponds to capital N equals to 1. By the way, the classical picture is embedded in this. Okay, if now your matrices have size 1 times 1, then you're in the complex field. Everything is as usual. And here Here, of course, these things disappear, but we cannot make them disappear in the general case, because if we multiply b by u and v, this will still be true here, because we are taking the norm. So we are taking, not exactly the norming functional. We are in the real setting, we would be taking the norming functional, and it's opposite. And that's the reason why we have this now uv, which in real geometry would be plus or minus the norming functional. And the crucial point, of course, in this smoothness property is that everything is uniform in the dimension. So the crucial thing here is that this bound here does not depend either actually on little n or on capital N. It depends on epsilon, but the spectral gap is fixed. That's OK. And so you have this function that is dimension-free, which controls this. So this is really an infinite dimensional smoothness property, because the normalizations, when they are done right, are the right ones for the problem. OK. So here is, along the same lines, an application that also has this same geometric flavor. It is analogous to the fact that when you consider the Euclidean sphere in dimension n, now you try to write your Euclidean norm as an equivalent to the soup of a certain number of functionals. You want to write your norm as the soup of a certain number of functionals up to a constant. Well, there's a theorem that requires, it's a nice statement. It requires a proof. Usually one uses measure theory, Gaussian measures, probability to prove it. That's my favorite proof somehow. There's a theorem that says, well, you cannot do this with too few functionals. You need an exponential number of functionals in the dimension. If you want to write the Euclidean norm, because it is a smooth norm, you need that. If you take, for instance, the L1 norm, okay, that's a bad choice. So if you take the L infinity norm, if you take the L infinity norm in dimension n, then you have n coordinates of which you're taking the soup. So n, or in the real, with real scalars, twice n functionals are enough. And so, but the L infinity n's corresponds to a ball which is, very flat, which is, not as nicely round as the ball of Hilbert space. And so in the matrix setting, this is the analogous result. And the analogous result is this. Suppose that I'm able to find a way to write the analog of my Euclidean norm as equivalent, like this, to the soup over something that is, in this setting, the generalization of, the modulus of a linear functional, which is formally this thing. At least the notation aim at making this clear. Then the conclusion is, again, you have an exponential number. But what's nice is that you get an exponential number in now the new dimension that counts. And of course, the relevant dimension now is n times capital N squared, because each scalar is a capital N times capital N matrix that has dimension capital N squared. So the real underlying dimension that you have to deal with is this one. This comes all along in this subject. So again, if n is equal to 1, we recover the statement that I've mentioned before. Again, going to the interference. So I think I've said this actually before. I should have maybe permuted the transparencies. I just found this nice picture on the web. I'm not sure it corresponds exactly, but of course the picture is that the analogous problem, okay, is you have a ball and you try to stick it as closely as you can in between, how to say, a polyhedron, okay, given with convex polyhedron with faces, and you want to count in geometric language, the minimum number of faces of polyhedron that are going to approximate your body, your convex body. And so what we just showed is exactly the matricial analog of roughly this picture here. So one can sort of start playing with all sorts of questions about polyhedron that are very interesting. There's, in this theory of operator spaces, there is a duality. So you have, for instance, relation between the number of faces and the number of vertices of a body and its dual, which actually are very natural to investigate in this new setting. But I don't have too much to say about that yet. So I use random methods, random matrices, and the starting point for me definitely is this beautiful result of Hastings that says that certainly there are, if you pick them at random, you will find plenty of spectral expanders, quantum expanders. So what he has is this: for any epsilon positive, if you take the uniform measure over n tuples of unitary matrices, so you use Haar measures on the unitary group, and then you take your little n unitaries independently, picked at random, so you look at the product of the n copies of the unitary group un, you look at the Haar measure on this group, and then you obtain that when capital N tends to infinity, the probability that you have, it's a very precise result. This bound for the crucial operator is 1. So the probability tends to 1. So it's very likely, if you pick them at random, that you find what you want. And this number, that's what's beautiful about the result, this number is best possible. And although for what I'm doing, what I really care about, you see, it's best possible, but in this framework, that is, you cannot prove this lemma with any number less than this number. But of course, you have to write the lemma as it is here with any epsilon. Okay? It's, however, I should say that for what I'm doing, what matters just is that this number gives us quantum expanders. So I only care to have a bound less than n, okay? Less than n times something less than 1. So in fact, the fact that it is square root of n doesn't really matter. What I care is that it is little o of n. Let me, however, show you, because I think this is pretty and it shows the connection of the subject with other questions. Let me show you why we have this number appearing here, which some of you obviously immediately recognized. So I just repeated the line. Why should we expect this number appearing here? Well, it's connected to random walks on the free group. This number appears already in this famous work of Kesten, which I think is actually his PhD thesis from the late 1950s, where he studied random walks on the free group. And the number appears as the spectral radius of the random walk. He works with symmetric sets of generators, so that number appears when n is an even integer in his work. Later, Ekman and Ostran generalized this. In any case, if you look at the free group on n generators, and you look at the left regular representation on the free group, and now you look at the generators, okay, the free generators of the group, this gives you unitary operators now on an infinite dimensional space, and I call them V1, Vn. Okay, so this is the translations by the free generators on L2 of the free group. So the classical fact is that the norm is equal to that, and the connection to this result is actually pretty precise, because it turns out that if you are familiar with how people in random matrix theory deal with the convergence of distributions of random matrices, they work with a random matrix, then they say, okay, this random matrix has a spectral distribution. here we are dealing with unitary matrices, so there's no question. We have clearly eigenvalues, etc., a spectral distribution, and you normalize it, of course, and this spectral distribution can possibly converge to something. That's the usual problem in random matrix theory. So here, it turns out that these distributions converge, their spectral distribution of these random matrices converge almost surely weakly in distribution, or here in moments, you will see what it means, to this infinite dimensional family V1, Vn. So the J here corresponds to the J here, but we want to work with the collection and somehow have, it's an analogous to a limit, in classical probability, they would call this multivariate limit theorem, I guess. So the family here converges to the family here in moments in the style that's well known from the work, in particular, of Voiculescu in free probability. So what it means precisely is this. We have a phenomenon algebra generated by V1, Vn. That's the phenomenon algebra of the free group. People in operator algebra call it the free group factor. It's equipped with a nice normalized trace given by this very simple expression. Delta E is the basis vector associated to the unit element of the free group. And then the norm, exactly like in the usual LP space over a probability, the L infinity norm is the sup, is the limit, the increasing limit of the LP norms over your probability space. And for traces, it's exactly the same. So the norm of your operator is the increasing limit of the LP tau norm, which corresponds to this. This corresponds to P equals to 2m. Okay, this is what you would define as the norm in LP. Okay, so I remind you here quickly that we now want to analyze, oops, that should be a z. There's a misprint here. So we want to, I changed x to z, I forgot this one. So I decided to call this zjn. So zjn is an n squared times n squared matrix. And the weak convergence that I'm talking about is a convergence that can be expressed by just restricting, like you do in probability theory. When you look at convergence in distribution, you would say, oh, any continuous bounded function applied to the sequence of probabilities tends to, the same thing with the limit probability. So here it's similar, just it turns out that we work just with polynomials, and in this setting, it can be extended to more general functions. Never mind. So Q is an arbitrary polynomial, but of course it's non-commutative probability, so non-commutative variables, and then we allow, we don't want to restrict to analytic, so we allow also anti-analytic. So these polynomials are polynomials in xj and xj star. And weak convergence just is, by definition, this convergence whenever Q is a monomial. Okay. So the weak convergence in this setting is actually a consequence of, easy consequence of known results. First, a result of Voiculescu that says that if you just select the unitaries, you don't bring this z up, you just look at the unitaries, then they converge to this free family Vj associated to the free generators in distribution, so in this weak moment condition. So that's Voiculescu's well-known result. And then the second observation is just a simple calculation with involving the trace when you compute the trace of an element. Well, it's written here. When you compute the trace of an element like that, you see, you will get the trace of this times the complex conjugate of the trace of this. So if it's A tensor A bar, you will get the modulus of the trace to the square. So that's what I wrote here. You get this thing minus 1 over n squared. So this thing, then the rest is not important. So this thing, you know what it converges to by the first point. Okay? Converges to tau of qvj. But you have this modulus to the square to worry about. But here, the miracle is that in fact, if you look at the free generators, then when Q is a monomial, and from monomials, of course, you get to polynomials, so you can restrict by linear, just linear span, you restrict to monomials. And if this is a monomial, then it turns out that just by obviously, when you compute, this is equal to 0 or 1, because it depends whether or not your word is trivial or not. If it's trivial, you get 0. If it's you get 1. If it's non-trivial, you get 0. And so modulus squared, you don't care. It's the same thing. And this correction by P is a projection of rank 1. So when you take the trace and in a space of large dimension, it's completely negligible. It disappears. And so that gives the result. We have this almost sure convergence to these. OK, so now we have these ZJs, which are I've rewritten here. And oops. We want to remind you that we're interested in comparing the norm of this with the norm of this. The norm being here the norm of a random element. So here is what can be done. You can, this is again classical type of manipulation in random matrix theory. You look at your p equals 2 to the, well, 2m, so you want an even integer for the value of p. You look at the limit inf of the norms of this guy. So this is greater than this because you have a probability. So LP norm is less than L infinity norm. And now the limit of these LP norms, these are moments because it involves just a certain monomials to compute this LP norm. You have the monomials x star x to power m, okay? And so you use this as your monomial Q, and it gives you that it is equal to that, okay? But now you can take the sup over all P, you see, in this line here, and so it gives you that this lim_inf is greater than the sup over all P, or the limit over all P, and that's the norm of T. So you get the lower bound. You get this lower bound, which is here, that this lim_inf is greater, and in fact, almost surely, because everything we did in the almost sure sense, this lim_inf is almost surely greater than 2 square root of n minus 1. So if you go back to Hastings' result, it tells you that there's no way you can make Hastings' result hold with a smaller number than this 2 square root of n minus 1. But I was happy to show you a complete proof of something, which as a rule is a good thing to do, but I must now confess that this is the easy direction. The Hastings result is actually quite complicated. It is pages long, and it's an upper bound. While here, what I showed you is what I call the easy lower bound in this result. So actually, I don't use Hastings' result in my paper. I cooked out a different way to relate it to results in free probability by Hagerup, Thornbjørnsen, and so on. And I relate it to Gaussian random matrices. I get a much quicker argument. So maybe now I should go a bit faster. So the approach I use is based on a comparison principle, and it is at the same time weaker and stronger than Hastings' result. It is weaker because I get a bound of the order, you see, constant times square root of n, while he gets this precise 2 square root of n minus 1. So it is less precise. But his result is asymptotic in capital N, and what I'm writing now is actually a uniform result for all n, capital N. And I skipped one part, so let me, for clarity, let me just insert it. I'm now shifting from an almost sure result to a result in the mean. So that might shock some of you, but in this subject, there is a so-called concentration of measure argument, which is inherent to the type of random objects we are studying. They are extremely concentrated, so that actually it's just as hard to bound the mean of the norm as to have good tail estimates on the deviation of the probability. So it all boils down to the mean. That's why I can concentrate on the mean of the norm. that's by concentration of measure, that's the key word. Okay, so all the results that I'm writing here, I have soft proofs of them if you're ready to accept results of Hagerup and Thornbjørnsen on the Gaussian case. I think I explained this here. They actually proved a finer estimate, but they proved something like this with, instead of ZJN, independent Gaussian random matrices. And I conjecture, I'm afraid this is recorded, so I'll have to accept that. I conjecture that, in fact, the ZJN satisfy the same kind of strong convergence. So whenever you have coefficients, you should get, in the limit, the same results with these free generators on the free group. This is motivated by several cases in the work of Camille Mal in France, where this kind of strong convergence was proved after Hagerup and Thornbjørnsen. And there's a very pretty recent paper by Benoit Collins, who's now a Japanese mathematician, and Camille Mal, who's still in France. They proved that this strong convergence that I'm conjecturing here for ZJN holds for UJN. So if you just select at random your unitaries, it's already quite non-trivial that you have this phenomenon. All I have proved is upper bound of the limit with a fixed constant, but I don't have, I don't have a precise limit result like this. That's just a conjecture. Okay. So I think I want to be quite quick about this. I have an application which is in a paper that will appear this year in Mathematica on, which is an amusing topic. Because I've worked on the metric entropy of compact sets in relation to the study of Gaussian processes in my, long ago in my youth. And I here went back to this by studying the metric entropy of, it's like, it's a super result in some sense. I study the metric entropy of the set of Banach spaces of a fixed dimension. And so I look at the complex, I look at the Banach-Mazur compactum, which is by definition the set of n-dimensional Banach spaces equipped with this object, this number, which is described usually as the Banach-Mazur distance. Distance should be, quote unquote, because the distance is multiplicative. So you have to everywhere put a log if you want to have really a distance and really a triangle inequality. But in practice, we don't do this. We keep working with these objects without bothering to transform everything to additive. And then all the notions are the same. So modulo the obvious identification of two spaces that are isometric to make this space Hausdorff, you have a compact metric space, a nice compact metric space. And it has it's well known, that's a result of Fritz John. It has a center, which is the Euclidean space with radius square root of n, and it has diameter n. And it is known that this diameter is optimal. And the classical facts that are here all have their analog in this object that I've introduced quickly before, this space OH, which is the operator space analog of Hilbert space. Everything written here is true. The last being much easier, actually. The diameter is n, but that's much easier. So the metric entropy of this metric space has been estimated. In fact, in the literature, there's a paper by Russian mathematician Bronstein who works on convex bodies, and he proved the following nice bound, which is about the entropy of this space, but that's for a fixed dimension and for small epsilon. It's actually not what I like, not what I need to use in my work, because I'm interested in asymptotically large dimension. Here the dimension is fixed. But this is definitely related to the subject I'm discussing, so I need to state it. And the theorem that I've proved, which is somehow I don't know how to say this, I was sort of led to prove this because I wanted to prove the analog for operator spaces and the matricial analog of this. And when I did this, I realized that no one had bothered about the Banach space case on the similar case. And so I wrote the paper, and after I wrote the paper, of course, people woke up and said, oh, no, I thought of this, etc. And so it turns out that part of the bounds actually were well known. Some of my friends warned me that they had thought of this earlier. So in particular, Sharek told me that with Joram Linton-Strauss, he had thought of this about 10 or maybe 20 years earlier, part of this bound here. And the lower bound, which is the most important one, also actually popped up in a recent paper independently by Lidwak, Rudelson, and Tomczak-Jägerman. They follow this method of random Banach spaces of Gluskin. And so you see the result is that you have a two-sided bound. The dimension, what's important is the dimension is arbitrary, and the constants are fixed. Okay? And so the result gives you this. And I will just give you one last time, out of time, so I'll just go to the last. To the last slide, which is the matricial analog. And so you can, I think, because you can easily yourself complete the setting. So I now replace little n dimensional spaces, okay, which are Cn, okay, with n scalars. I do the same transformation as before. Now scalars are replaced by matrices, and I ask myself the same problem, but the distance is the distance dn, where instead of using scalars, I use matrices of size capital N times capital N. And so the result is similar. We have a two-sided bound for the metric entropy of this object. And it measures a certain explosion of the set of n-dimensional operator spaces. This is sort of, I'm out of time, so I'm just stick to that. Measures this, a certain explosion of this space, which is related to a phenomenon called the lack of exactness, possible exactness for operator spaces. So in short, the Banach-Mazur compactum is compact. It's a compact metric space. And if you go to this matrix analog, then you find a space which is not compact. It still is a complete metric space, but it's not compact. And actually, we proved it's not even separable. We proved with Junger it's not even separable. So this theorem is related to a research that tries to measure the degree of growth of this huge monster, which is the set of n-dimensional, but this little n fixed, okay, set of n-dimensional operator spaces is a huge space, and this measures, in a certain sense, its growth. Thank you very much.
So every reducible representation of the unitary group UN is parameterized by a pair of Young diagrams. So in your case, you were working on the tensor product of the defining representation and its compressed conjugate representation. So it's split into a trivial and non-trivial. So you plug in the random matrix in that representation. So, but you can play the same game. You start with an arbitrary pair of Lagrange diagrams. You plug in unitary random matrices. You consider polynomial, and then you estimate norm. You can do the same game for the other pair of diagrams. The question is, can you do the same thing for other representations?
But can you do what? You see, this is of course what it depends what you're asking. I'm sort of here, you know. This is all very, how to say, in some sense, very rough. But I'm just interested in producing the extreme behaviors. So what I suspect I've caught it. That is, I suspect one thing that will be proved is that, you know, if you don't take a representation that looks like the, how do you call it, standard or something, or for UN, the inclusion representation, I don't know what name. If you don't take this, you won't get as many, anyway, you won't get as many quantum expanders. This is more or less, it's more or less the philosophy.
It's not really about quantum expanders.
Okay.
Yeah, that's for sure. But still you get the same limit norm. I mean, the square root of n minus thing.
Ah, yeah, okay. Okay. Oh no, then the question about the limit theorem, yeah, that of course is quite interesting. Yeah.
Actually, I once asked Noah about that question.
Yeah,
And
I see.
He got interested in
I also asked him. and Mal, I think they were together in Lyon last year. We discussed it, but for me, and I told him that for me it's the strong convergence that has applications, because in random matrix theory they actually often are happy with estimating the asymptotic distribution of the eigenvalues, etc., which they call the bulk of the spectrum in their jargon. And I want the edge of the spectrum. I want the operator norm of this random matrix to be controlled in the limit. So I want really to nail the upper bound of the spectrum. But you're making it more complicated, of course. This is the beginning.
In the Hastings lemma, there's an epsilon, but we don't know if this epsilon is necessary with epsilon 0.
Something, of course. Oh, epsilon 0? Or epsilon 0?
Epsilon 0 is correct or
Oh, my feeling is, no, it can't be, but but I need to make sure. But I thought you were going to ask. This of course is interesting. Whether you could put in his calculation. It's very, very hard already to get to this level. But it would be nice to have an epsilon depending on n. Some sort of term, or maybe an epsilon times square root of n, which would be extremely good, but that would almost be the conjecture. Actually, that would be the conjecture, essentially. Yeah.
You had this question about the bounds on a number of irreducible representations of the Kyoto upper dimension bound. What is the best known bound you were talking about? The lower bound?
Yes, it's embarrassing. It's embarrassing. I haven't really, so the known sort of families of expanders, anyway, the ones I know, are either the ones from SL3, Z, ZP, or Kasabov's work on permutation groups, which gives the streak. And in both cases, it is very, very small, what you get. You have to take a soup. So if you take, it's a little bit tricky to know what exactly you're talking about, even if you take permutation groups, because you're only fixing the number of generators in the spectral gap. So it's not clear what will be the size of the permutation groups that will give you the largest number of Young diagrams with a certain, it's actually, when you write what this number is about, it is to me, it's not at all clear. So I'm embarrassed to answer your question. I've, by email, asked around specialists and did not get much answer. So I think from the say, rough estimates, you get something like n squared or something like that. Very, very far from exponential. If you want to have really, the spectral gap as usual and with a fixed degree. Because they, Schulam and Vigdersen, as I said, the degree is not fixed, so it's kind of, they say it's probably exponential, but they do an iteration and they get degrees that grow very, very, very slowly compared to the growth of the exponential, so they conclude that it's essentially, it's actually not an exponential lower bound.